Okay. Okay, so oh, more folks are showing up. Let me go find. I was just looking at this email. I have to find a better way to do this. DC. There we go. Yeah, so welcome to Coffee Compiler Club. I'm recording, and I'll let the recording be live pretty soon, shortly about an hour or two after the meeting. And if you're not good with that, then bail out and watch the show post afterwards. There's no set agenda. We kind of leave it in the compilers and language implementations, runtimes, type systems, GC, garbage collection. Someone specifically said I wanted to talk about register allocation this go around, and I don't know if they're here yet. Thank you, Mullen. After that, it's just sort of like, whatever you want. We're live and let's roll. Let me see if I can find the note on I want to talk about register allocation and see if this person is present. And see, I don't think they're here, so fine. Whatever people want to talk about, we can go down to register allocation early. We can talk about SSA. The SSA is probably a good thing. So Cameron can chime in now, so it'll be a good experience. Who here does not know about SSA? How about that's the wrong way to ask it. So who here knows about SSA? And I don't care if you say yes or put it in the chat. And it's a big silence either way because no one will answer any questions unless they're burning. Who here will raise their hands if I ask you to? Okay, so just so you know, if I go into an audience with 1,000 people, oh, I saw some hand raises go up there, and I say, try to get a question answered. If you're in Europe, it's like nobody. There's some more. Fine. So now, was that raise your hand to know nothing, or raise your hand because you want to know something? Yeah, exactly. Fine. Oh, people finding the hand raise thing, and it just shows for like a fraction of a second. I can't see it and clear it. It's kind of obnoxious. Yeah. Why do I care? So using it soon, yes. So SSA, the reason I'm going to bring it up until we have somebody else has a different topic just to roll along here. SSA is, in my opinion, the largest single improvement to compiler technology in the last 20 years. Static single assignment, it means all your representations have statically a single assignment to variables. So whatever variables you have in your program, you rename them uniquely such that every variable gets assigned once. And in particular, it gets weird when you have an if then else diamond where you assign X to either side, you assign it to true or to false, and you have a merge point. It's resolved by putting in a bogus function, a fake function called a phi or phi function, which merges the X0 and the X1 and makes a new variable X2 at the merge point.
And supposedly the name phi comes originally from IBM, where they developed it. They called it phony functions, and they eventually renamed it to phi.
I did not know that. There you go. I have a fair amount of compiler history in my head, but apparently not everything. It's all good.
I read it all last weekend, so.
Yeah. So the main advantage to SSA is because of the single assignment property, the value of a variable is known to be the one and only thing assigned to it. And from a sort of classic SSA format, which you can do sort of with like tuples in a standard compiler, you can convert to a graphical format very directly. Right, so some people talking about SSA in LLVM. From the graph format of things, a lot of algorithms which would require multiple order in passes can be done in a single order in pass or can be done incrementally. And this is what Hotspot's been doing for 25 years inside the Java VM, and what the Graal folks picked up on, and some other folks have picked up on it, and now LLVM. People have been using SSA for a long time, the thing that Hotspot did was went to SSA early and stayed in it the whole time. And obviously you can write a large, fast optimizing compiler using SSA all the time and never coming out of SSA form. And it works well and it's reliable and fast and blah, blah, blah. It has all the right properties. So if you're going to write a compiler, I would highly recommend going into SSA right up front and staying there. If you're using somebody else's compiler and they start using SSA, you'll have to deal with going in and out and in and out and in and out of SSA form for a while, and that's kind of a pain in the neck. Because of the representation change, you typically have debugging issues that span a flip in and out of SSA form that require some pain in the neck to sort out. So that's my opinion. Go to SSA all the time and stay there. Ta-da!
So in LLVM, there is one trick, or really it's a documented approach. They also recommend this in the tutorial, is to not necessarily convert to SSA yourself, but only use stack instructions, loads and stores. And then one of the very first passes in LLVM, there are actually two passes to do that. The documentation only mentions mem to reg, which is of course memory to register, and that's going to convert your code to SSA form. But actually also and I didn't know about it initially, it's the scalar replacement of aggregates. This is not what the name would necessarily suggest, because I was thinking that it is only so literally for aggregates like structs, but it literally also converts the loads and stores for ordinary scalars, replacing scalars with registers. So the name is a bit misleading, I think. I don't know the history about it. I'm pretty sure they started with mem to reg only. And the convenience is that it's pretty easy to mess up some of the fnodes insertions yourself, but if you rely on those passes, mem to reg and throw, you can write pretty much dump code. It's actually very, very clear that it's a dump code. If you have ever seen the O0 assembly code generated by client, you probably notice that it looks really, really silly, because it keeps storing and reloading the exact same value from the exact same register, and this is why. Because
we call it the Scala compiler. Yep.
Exactly. It's
like, hey, Lisa,
I think it's even in a sense dumber than what Turbo C or Turbo C++ did. I remember that those compilers, when you run at low optimization levels, you still had some register allocation being done in Turbo C or Turbo C++. But
so Matt, what are you working on with LLVM? What gives you this insight?
Right now, I cannot talk about it because I will only know more this summer, but I'm going to be working in commercially with LLVM starting later this summer. So far, that has been my own preparation.
Wow. So you took a job, you don't know who you're working for or what you're doing?
No, I know. I just don't want to talk about it before it's finalized. Yeah.
Fine.
And the thing is, the IR in LLVM, it's an SSA form, but and it's all the way SSA. But you can have a locus and you can have load stores initially, just to simplify your front end and rely on the existing SSA construction essentially.
Yeah. Okay.
That's good to know, because I wasn't looking forward to having to convert everything myself to SSA. So,
You're using LLVM too?
Me?
Yeah, Cameron.
But that's the goal. Yeah.
Okay. Yeah.
So we have our own IR. It's a compact, network ready IR. But what we'll do is we'll produce LLVM IR. So the main thing I still have to figure out, which I don't know, Artur, if you or Matt has any experience with this, is how to reload and backpatch with LLVM. How much of that is built in?
I know the Azul folks have been using it for Java, so they have to have some way to deal with compilation, runtime compilation units.
Well, what we do, we take the object file produced by LLVM, we just parse it and plug it into VM structures, and we don't use any existing LLVM support for batching or dynamic execution.
Does it have any built-in, or?
There is something. I think it's called org.jit and in general LLVM JIT, but I have zero experience with it. And can you explain a little bit what exactly you want to do?
Yeah, an adaptive runtime profiling compiler. a la hotspot, but for a different instruction set.
This is a cloud-based thing.
Right.
Yeah, distributed computing.
Essentially, you want to use LLVM to compile stuff, and then you want to be able to patch it and to like manage lifecycle of this code, things like that.
Yep, exactly.
You need a runtime.
I need a
using the
runtime.
JVM for runtime or not?
No, just temporarily. So we use the JVM today, but it's
You got a runtime to build. That's a big ass piece of work.
Yeah, I know.
I did the runtime for, big chunks of the runtime for Sun, and I did bigger chunks of the runtime for Azul, and there's a lot of stuff there.
Yeah, but it's easier the third time.
It's true. You got funding.
It turns out I do.
Maybe we should take this conversation offline.
Oh no, not that.
I'm not
much
looking for a job though.
No, I'm talking about a small check Larry wrote to me a few years ago.
Okay.
I thought you knew what we were doing.
Oh, I didn't realize that you were doing your own runtime. I just assumed you're going to take a JVM and you
No, JVM sucks for what we're doing. Like we have a completely different runtime model. So we make it look like Java, but the runtime model is a bunch of single-threaded machines.
Okay, because I did the distributed computing for H2O, and that was all JVMs. And we passed code around with bytecodes, over the wire. After the cluster was up, somebody had some bytecodes, they handed it around to everybody else.
Yeah, I'm planning to support 32 terabyte heaps with no garbage collection pauses, I don't want any barriers, memory barriers, except where mutable domains intersect each other.
Yeah, but we should have that conversation about that then, because there are, I've been down the large heap, low memory pause, garbage collection thing, a long time at Azul.
Right, but you were doing that for Java, and Java has one heap conceptually. It has one giant shared mutable. Everyone hack at it with your hammer.
I also did a per thread GC for garbage collecting stack allocatable things.
Right.
That was one of the fun side effects that came out. And the answer was, it was good on memory bandwidth, but it didn't beat the background GC, which just burned background cycles, which x86 is swimming in.
Yeah. So what I've got designed is that I'll actually inflate the stack frames to hold. So if I can get stack analysis to be fairly good, escape analysis to be fairly good, I can pre-inflate the stack frames with extra space for the things that escape nested frames, and then basically it becomes an alloc instead of even a slab allocator.
I have a fairly, I was going to say fairly unique, a fairly heavy experience in this area.
I know, that's why I'm on the phone.
Well, do you want to hear what you're going to run up against?
Yes, I do.
Okay, so the first thing that happens is the escape analysis fails reliably. You will not get an interesting number of things to not escape because there's so many weird ass paths where shit escapes that you don't care about. However, when things run, the actual count of escaping objects, they fall into a couple of different categories, but you can get a fair number of things to not escape. So what I ended up implementing was escape detection, not escape analysis.
Yep, that's our plan.
Okay. The detection phrase definitely had issues with stack frames that would be of variable sizes, and they would, depending on where you landed in the call chain, different frames had to have more or less space to do an alloc style allocation. You also had things that were stack allocated, but the stack ran down a ways and then spun, and you never unwound because you're running a server loop. Mm-hmm. And so things stayed permanently allocated. You eventually wanted to migrate them to some background GC so you didn't have to rewalk them. You had things that were leaking in a loop so that you ran out of any amount of stack space, however big your stack was. Unless your stack was your terabytes, it's going to run out. So you had to have a way to evict things and just give it up because it was leaking. And now, unless you have leak semantics that are special, you're going to run out of memory eventually, but eventually it could be a very long time. You really wanted to do reclamation per loop, not per function call. Function call in and out is not exciting per se, other than it's a clean, easy breakpoint. But what really happens is you want to take all the allocations that happen in a loop and reclaim it for the next go round on the loop. That's the big win.
Yep.
So having said all that, that required a read barrier and a write barrier. Those barriers could be baked down on an x86 to being extremely cheap. They're not zero.
What were the barriers for? They were for other threads or for not other threads? That was just for this
No,
thread.
they were for detecting when you were escaping something. So you walked up out of a function and you returned a pointer that was previously allocated too low. So when you allocate, where in the stack frames, you have a pile of stack frames, where do you allocate it?
You'll actually allocate it in a previous frame.
Which one? So you can't answer that because you have some factory, and somewhere down in here, he's allocating with a lifetime. It must be up here. So he's going to unwind and escape that pointer up to here, but maybe it never escapes again. And now when this frame goes, you get your storage back, but maybe it does escape again. And you don't know where the right place to go put that allocation is because your escape analysis just fails. So you guess, and you guess wrong. So you have to correct. So that's the detection part. Did I get the right frame? If not, I have to push it up a frame.
So theoretically, though, couldn't you use this, couldn't you base your decisions on actual runtime behavior that you've already witnessed?
That's what I'm doing.
Okay.
I have a runtime behavior. I started it, I could start it more conservative, but wherever I started it, I always guessed wrong. So as soon as you always guess wrong, at some point, you have to have a correction mechanism. As soon as you have a correction mechanism, you might as well be aggressive and fucking correct for the beginning. It's just like JITting. You count things for a while, and then you go do shit. Okay, so here you count what frame, how many frames backwards you want to go for a while, and then you make your guess, and you start allocating that far back, and that frame's not big enough, so you have to do some overflow on it, and yada, yada, and you screw around for a while. Once that stabilizes, I could get roughly 70% of all allocations on a JBoss, busy JBoss, to do the right thing. So 70% of all allocations being stack allocated sounds like a big win, and it wasn't big enough. At least not compared to the background GC. Part of that was when I did a stack GC, it still cost me for on that stack to do a stack GC, and I needed to offload that work to another thread. Stack GCs were a lot cheaper than main GCs. Mostly it's hot in your cache, except for all the bad cases where it's not, and that's where you have to offload shit. All the leaking stuff that went away, all the things that somebody comes along and says, oh, I need a 10 gigabyte array. Well, you're not gonna put that in your stack. So it goes off somewhere else. It goes, you want it to go into large object heap memories allocation, or somebody says 10 gigs, well, I'll just do it lazily using TOBs to zero things out on you, and I don't have to actually zero 10 gigs worth of pages, right? And then, I'm running a big data machine learning thing or whatever, and I have some giant arrays that come and go and come and go. So there's a bunch of work to be done there to make a decent stack GC. You can get pretty far as soon as you have any cross-thread anything, and of course in Java land you have a bunch of junk ones that come right away. But as soon as you have any cross-thread anything, you have to support also escape to heap, right, which means you took an object that's on your stack and you rewrote it out to the heap.
Yep. And we have that anyway because we have, as you were talking last week, we do the same thing with closures. You can close over read-write values as well, including local read. So each variable that we have is actually an object. Now, right, it's a free object, so if you don't ask for it, it's not an object. But as soon as you ask for it, it exists, right?
Yeah, right.
And when you ask for it, it exists, but it actually doesn't, because at this point, it's just functions pretending to be an object, right? But if it happens to survive because you've closed over it and someone else takes that closure, so if your closure escapes, then it actually has to lift it. Well, it has to do one of two things. It either lifts it out of the frame or the frame can't get collected. So depending on what we do for continuation, so our runtime model is basically mutable domains of information that represent a single-threaded von Neumann machine, right? So only one thread at a time can hit any of that mutable data. And that mutable data is not visible from outside that domain except by creating execution within the domain. So think about it as kind of async await. If I make a call into that domain,
Actor model.
yes, yeah, except I didn't know what that was when I started.
Okay.
So when you, it's kind of Erlangish, yes.
Yeah.
It's very Erlangish actually. So you hit, and I didn't know much about Erlang either, but so you hit reference to something in that domain. The reference that you have from the outside is necessarily a proxy. So your execution is proxied into it. Now that may be basically zero cost. It doesn't have to be a message. It doesn't have to be asynchronous.
Well, there's a flow rate that you can support message in and out as long as you're below the flow rate. Your one worker thread is supporting all of the.
Well, it's not a real thread. That's the point. I don't actually have to.
You're claiming single-threaded von Neumann machine access model.
I'm claiming at most one thread will be executing within what we call a service, which is this mutable domain. At most one at a time. But there can be many fibers, because if any of those executing things in there go to another contended service, then this becomes reentrable, unless it's been marked as not reentrable. I mean, that's configurable. But this domain, that fiber then goes to sleep on this domain, and another request can come in and execute.
So what do you do with, like, the classic example of caching, concurrent caching? I have a bunch of guys, 99% are reads, 1% are updates.
Yep.
What's the parallel support model for 99% reads, 1% updates?
Well, first of all, you could basically map the coherence partitioned implementation on top of services. So instead of a bucket, it's a service. So one of these mutable domains is a service, but the data in the cache itself could be immutable, because immutable data is allowed to flow through the barrier, through that service barrier.
No, but
so
I'm talking about updates too. So you do the copy on write update model, the immutable data only ever model.
So the only thing that can go through that barrier is a proxy or an immutable piece of data. So if you think about the memory hierarchy, it's not a single heap shared by every thread where they're all banging away on the same data structure. Instead, each service has its own mutable heap and possibly its own immutable heap. But services are arranged hierarchically so that a collection of services becomes what's called a container. And a container maps one-to-one with a type system. So when we formalize a type system, which is an immutable thing, so it's not like Java where it discovers the type system accidentally on the fly and rewrites all the code every time it finds a new thing. So the type system is transitively closed over, and that container that hosts that type system, and I could have more than one container for the same type system, but a container itself has an immutable heap. And then because the container is a service, it has its own mutable heap as well. So basically containers are then arranged hierarchically. So if a container has to talk to another container, I only have to escalate the immutable data to the intersection of those two containers if it has to survive the execution.
I guess I'm asking a different question, which is how do you support a high flow rate where you have mutations on an individual element at the base? So the obvious strategies are I lock, and it's single threaded, but I lock readers and writers. I have a read-write lock semantics, multiple readers, one writer. You have to watch for starvation. I have a entirely concurrent lock-free algorithm. What's the strategy?
So the goal is to actually support pretty much all those. So messaging, locks, and lock-free, but it's all decided at runtime based on statistics. So the programming model appears that you're just making a call into another service, which may be a compare and swap call, for example, and then a compare and swap style call, and then at runtime, based on contention. So we keep statistics on contention. So basically what we're trying to do is just use a hotspot style concept for threading, right? So if I have a highly contended service where everyone's coming from different directions and hammering it, I may actually allocate an entire hardware core for that one service.
Yeah, and what I'm saying, what happens when that one core is not enough?
Then we're
This
screwed.
is a model I'm in all the time.
No, I mean that's the limit of the architecture. Is
Okay,
it's intended to be, you know, as fast as one core.
Okay.
No, you got to pick your limits, right?
Well, no. But the reason I'm bringing it up is that, you know, as soon as I said cache, where it's 99% read, one write, that's a sort of a standard model people use to support heavily caching web pages, web portals, all kinds of domains. I do this all kind of crap in machine learning for distributed models. There's a bunch of that stuff where you have a very small percentage of writes, which as soon as you go to a shared memory concurrent data structure, you can handle it because the shared memory supports all the cores all the time, or up to, you know, 50, however many you got in your x86. And so you get another order of magnitude more performance out. If the rate at which you do updates is modest enough, then having the you know, reader only lock, reader writer lock works very well. And the implementation of reader writer lock
we don't expose locks at all. So there's no wait, there's no notify, there's no synchronize, there's no lock. But that service, that mutable domain, can be as small as a single word.
Right. So I'm talking about, I have a service which is supporting a cache. I'm handed keys, I hand out values, or I'm handed a key and a value and I mutate the state.
That's right. That's how we do it.
And what does that service implementation look like? Is there any restrictions on it? That's just some, you know, I wrote some hand rolled assembly for that service.
It looks like you're writing a single threaded map because it's only going to execute one of those at a time. So even though other services are calling into it, only one of those will execute at a time.
Yeah, and that, my point there was simply that can be a fairly hefty scaling bottleneck if I want to have a lot of folks banging on a shared common cache and most things successfully hit in the cache. I want to have a bazillion readers parallel read.
Yep.
Right. And so I'm asking, what is the model? What do I declare? Is there a way to declare that this service supports a crap ton of readers, but if a writer comes along, that's special and somehow we do something different?
So you wouldn't actually make it you wouldn't make that a service. You'd actually make that an immutable. And then behind the scenes, that immutable would use services. Basically, think of it this way: that the representation of the map is immutable, so it can be hammered on by any number of services at the same time. But
the representation of the map is mutable by the writers.
No, I meant the object that actually implements the map interface.
Yes. Okay, fine.
So that you could hand it out to 1,000 or 10,000 different services to hammer away.
What they all funnel into, I'm asking, they're funneling into one x86 core.
No, because it's immutable. That code can execute on all 1,000 cores at the same time because it has no mutable state of its own. But it does have, for example, it could have an immutable array of 1,024 services. Remember, the two things that the two magic items are mutable values and service proxies. So I can now have a distributed cache across those, you know, well, don't use 1,024, it's not prime, 1021.
Oh, I do prime sized caches all the time.
Yeah,
hash tables all the time.
I think 1021 is prime.
I'm sorry, I use power of 2 size hash tables all the time. Because of the mod function, if you're counting clock cycles, mod beats, you know.
Yeah, but mod is down to like 5 cycles now, and it can run inside a single core. So it's like those cycles.
So can and.
Yeah, memory miss is like 190 cycles, and a mod is 5, so we're good.
Fine.
You're probably right because you know it better than I do, but I've always just assumed.
I'm still concerned about. I'm just pointing out that the mod and prime size is not a requirement for a highly efficient, highly productive hash table. It certainly can be done that way. I certainly do it the other way on a regular basis with good experience. But it's less important than your counting cache misses.
So and just for the record, string hash code kills them both. So.
Well, you know. Wow.
Because you're streaming through the entire string. So you're flushing your entire L1 just to do a hash code.
Well, I'm thinking the strings are typically not long, but if somebody hands you a terabyte string, yeah.
So I've actually seen the dumps, the memory dumps from Oracle's various products that they sell. And the strings are all long and everything's in a hash table. And everything's a string, so.
All right. Well, they do cache hashes, so they only have to do it once.
Yep, that's true. But that's if you intern. So if it's not an intern string.
No. If you make a new every time, that's a classic bad fail, an independent bad fail. If you've made the damn string once and you get to reuse it a bunch, you win on the hash code, but you still have to freaking compare the entire length of the string body. If you're making strings every time, there's your problem, right there.
So basically to go back to the earlier conversation, obviously, if you're trying to make something that's going to keep 1,000 cores busy hammering away at one mutable data structure, you're not going to assign that to a typical developer.
Fine.
And so.
Well, I'm just proposing that you stare hard at what I consider to be a common use case of 1,000 readers and the occasional writer. That makes sure that works efficiently and well, whatever.
Sure, I'm with you. That's the, so if you think about, in Java, you have the ability to make a field atomic, for example. But I mean, you could just use an atomic int or something, but it's actually far better to actually make the field atomic. That concept itself in Ecstasy can be a service.
Right. No, I get where your services are at. That's not where I was. Yeah, that's fine.
Yeah, so basically what I say service, they just replace that with Erlang process, and that should map pretty well.
Pretty close, yeah. One of the fun games I played at H2O was trying to write code in a way that supported distributed parallel computation. And you get into the whole model of how do I talk about a parallel computation? And Doug Lee says fork join, and there's the stream people where we're parallel within the stream, and then there's the actor model. And if you're JavaScript, you get into the callback hell, which is basically it's really continuation passing style.
Yep.
So we ended up with something that looked like continuation passing style, and performance was extremely good. And coding would not have been ugly if we could have had any compiler support out of Java, but we had no boilerplate support. So there was a boilerplate action you had to take when you were calling to a blocking call, and we could tell you in the Java type system even this was a blocking call, but you had to still do some boilerplate magic. And as a consequence, it was easy to make a mistake. And so that was sort of the major grief. But if you didn't make any mistakes around the boilerplate, it was kind of straightforward then to write parallel code. And we would just, let's say parallel would distribute as well. That was part of the H2O magic.
Yep.
That's still in my head an open question of what's a good way to write parallel code. And actors seems like a one of the good ways. If you get the performance there, actors are one of the, in my opinion, look like one of the good ways to go.
Great.
I think Clojure does references that are software transactional memory atomic, which is another interesting approach. You name the things that are going to be parallel or referenced by more than one core. And because you name them, you can do a software transactional memory on the name set, which is small. And that was the old software transactional memories. STMs were always sucking because they didn't have a name set. So they conservatively did everything, and that was too much performance.
So you mentioned the boilerplate thing. I don't actually have a corresponding thing in my head to know exactly what you mean by that.
Well, if you look at JavaScript and you have await async, in a way that's a boilerplate that says, and here I block and I'll wake up on a different thread, but I don't really care, and I'll carry forward. So I write single threaded looking code, but there's a point where there's a blocking call being made, and then I'll switch threads, fibers, whatever the hell you want to call them, on the return. And because I want to do something else. Meanwhile, the code above is atomically executed on one core, and the code below is atomically executed on one core, But across the call, things can flip because an asynchronous call happens. I blocked here, and now something else happens. So you had to be aware of that crossing point. And what happened at H2O worked out fairly nicely. JavaScript is kind of okay there. Elm, that's more like an Elm model. The Elm model says all your blocking points are expressly the end of a computation, and you couldn't write code that's sort of back to back with a block out and come back so conveniently in Elm. But as a consequence, it's very obvious that when you took an asynchronous call and you didn't know when you were coming back, and when you came back, you carried forward on the second half of your conversation, but you otherwise wrote single-threaded code. Mm-hmm. And so it was very simple to write the single-threaded code and think about it, even as asynchronous calls were like banging in.
Yeah. So the challenge that so if you go back to your earlier question about highly concurrent data structure, the challenge that we have is that a closure usually is immutable and thus can actually go into, let's say I have 1,021 different buckets. I could actually take the same closure and execute it in parallel across all 1,021 buckets on 1,021 different cores on the chip that AMD releases in 3 years, right? So the downside, and this is what I was asking about the boilerplate because I wasn't sure if you had the same issue, is that if I close over something that's not immutable, so if I partially bind a function, for example, and I'm binding it to something that is in its graph is not immutable, then that function closure becomes not immutable, and thus it can't actually permeate, it can't get through the service boundary for the 1,021 buckets. So in reality, the code looks the same, but it actually has to suck the data out to process it. So it becomes a 1,021 times plus cache drain slower. So
right. Yeah, so H2O did a little different there. We had core math shit that mathematicians were writing and no systems-y stuff. And that was basically, you wrote the inner loop that was single-threaded for an inner loop, and we would auto-parallel and distribute that piece. And then we had systems-y stuff written by systems engineers who had to understand distributed computing. And they got the game where I had a piece of Java code and I had a breakpoint, and then I picked it up again because of the asynchronous nature of things. And in any amount of time might happen between, and threads might happen between, and I had to understand that the memory model might have changed values across that boundary because of the asynchronous nature. And it wasn't too bad, but it would have been a lot easier with the right boilerplate. But we were hand rolling the things that you're talking about, closures escaped or not. We declared them by hand. They escaped or they did not. If they did not, it was pure Java code and it was inline, and you just inlined it. If it was going to escape in that way, you went to a different data structure. You put it in specifically the key value store, which was distributed and parallel and did all the right things. And then you talked to it as if it were a service. You had getters and putters, and you got values out that may have mutated, and so you had to go ask again. So it was a model where the programmer declared every individual closure to be, escaping or not, parallel or not. And if they were not, you could write it like Java code and you're done. And if they were, you had to change coding styles.
So I guess the other flip side of that, and no one else is saying anything. So either they're really enjoying this conversation, or this is like so far off that they're like, what are these guys talking about? The other thing I really want to figure out, because, the last time I did fibers was like 15 years ago. And back then POSIX actually supported it, and they since removed it. It was called set.
Name's not important. Set
pointer or something. It was part of the POSIX API, but it was only in there for 2 years, and then they removed it. Artur, you probably know this. So LLVM though has some sort of fiber support. So does anyone have experience with the LLVM fiber support? Because at some point I'm either depending on LLVM to actually work, and it doesn't, and I'm screwed, or
fiber.
It
Go
is related. Not sure if this is what you're looking for, but LLVM also has coroutines.
Yes, that is related.
And
It's related, but it's not fibers.
it's not fibers, exactly. Fibers is something different, and it's. There's been very long discussion how coroutines are very, very, very different than fibers. But if it is something that it could also be obvious, then there are actually two forms of coroutines in LLVM. One is for the purposes of C++ frontend, Clang. The other one is for the purposes of Swift-C, which is the Swift frontend.
That's the one I was looking at, I think. Yeah.
So Clang or C++ does the state machine-based transformation. That's the one I'm slightly more familiar with, whereas Swift actually does continuation-based transformation.
Mm-hmm.
And they have different trade-offs. I do know that, for example, in C++, you can entirely elide heap allocation. So if you have a coroutine frame that is going to coroutine frame, that is going to coroutine frame and returning, you can all collapse that down to a single stack allocation, and you will never have to actually allocate the coroutine frame separately. Restrictions apply. But Swift, I remember they had some advantages. I actually know the third way they discuss pros and cons. So if you give me a moment, I can give the link.
That would be awesome. Yeah. And these were all like, because what we had before, like I'm going to really date myself here, but if you went back another 10 years, all we had was long jump. That was like the only.
Oh, yeah. There are plenty of those inside of Hotspot.
Well, you use those for exceptions, right?
Yeah.
So,
a lot of exception catching going on in Hotspot.
Okay, so I posted a link. This is mostly C++ oriented. However, let's see if I can find it. Okay, if you opened this page, then it's gonna be easier to say which part is which. So if you scroll down to talks 2018, then if you go to 2018 LLVM developers meeting, there is a talk by John McCall, coroutine representations and ABIs in LLVM. So he works on Swift compiler, and I think he's responsible for the Swift coroutines implementation, but he also compares and contrasts this with C++. So this is a pretty good code because it shows.
What was the name?
So it's 2018 talk by John McCall, coroutine representations and ABIs in LLVM.
Yeah, I found it.
It's pretty short. It's like 26 minutes.
I pasted the link into the chat.
Yep. That's that. Exactly.
So, besides Matt and Artur, who else has used LLVM? Cliff, have you even used it?
I have not.
Yeah, because I mean, you kind of just write your own anytime you want. Show off.
I don't write them that often, but I guess I did when I was younger. I wrote almost half a dozen sort of full-blown, all bells and whistles compilers when I was younger. Register allocation, code selection, parsing, everything, optimization. After Hotspot, it slowed way down.
You're too busy talking about it.
Yeah, well, people loved it, so I enjoyed talking. People enjoyed listening. Fine.
Yeah, no kidding. Anyone else? Like, how many people do we have today?
We have 14. I'm like settling in between, 15 to 20 is sort of the current average. It's a little more last week, a little less the week before, a lot more the week before, whatever.
Kind of stepping into the discussion you guys are having, was trying to follow along with the fibers and coroutines thing. Does anyone know how the Go routines differ from either of these, or are they similar? Because Go routines are like a core part of Go's, threading model. So. And as far as I understand, they're similar to fibers, but.
I am reading from, Stack Overflow. Is a Go routine a coroutine?
Oh, okay. Well, I should have.
30 seconds of Google search, Stack Overflow, bang. So there's people claiming they're slightly different.
So what is the real difference between, say, fibers or coroutines, or,
you know, I'm been reading. I'll have to read a bunch, look for like concise differences, but the baked in things have the property that they're a lot smoother to use. Everyone is attempting to do a game where if you take a blocking call, you don't do a heavyweight operation, you do a lightweight operation, whatever that is. So in the land of H2O, I'm using Douglas fork join, which basically gives me fiber-like behaviors on Java threads. I have tasks. A thread is running a task. A thread can block. That sucks. That's actually expensive. But I have lots of spare threads. The spare thread picks up the task, the next task in the task queue and runs. So it behaves similar to a fiber setup. Always the game being played there is you're trying to, a thread is considered fairly heavyweight these days, has a lots of interesting state, and blocking it means you lost a big resource. And the baked in coroutines, go routines and the like, typically threads are a lot cheaper, and when they block, you lose a cheaper resource. In addition, it's not the OS that wakes up the next thread, but the runtime does a handoff. So a common implementation strategy is the current user mode thread never talks to the OS, sees the blocking call, sets it off on some sort of backgroundy situation with an async return, and then goes back to his work queue, grabs the next piece of work, and carries on.
Yeah.
So there's no user mode context loss, but you did change what you were doing, and that may mean your caches get hammered because the new thing is not the same as the old thing. But saving the OS context switch is sort of a big win.
I looked at a dissection once of the Go routines, and this may be out of date, but it was actually more like what Cliff is talking about, where they were basically rewriting the code of the Go routine into a state machine that could be interleaved with the calling code. So, but at the same time, if you look at the, and I've only used Go for a week, that's all I could bear. If you look at the actual construction of the Go routine concept, it is quite easy to imagine that it could be executed in parallel. So for example, one of the thoughts that I had was that, you know, with hyperthreading, particularly with the cache impact from hyperthreading, you could run a Go routine on the fake core of the, so you could basically run in parallel, whichever one's faster, you would swap them back, you would put on the, whichever one uses more resources, you would put on the 0, and whichever one is less intrusive, you would put on the 1. And basically then you'd have 2 parallel threads running on one core, and then you could spin, you could cheap spin on the, whichever one is waiting for the other.
So you don't cheap spin. The first man out flips a atomic bit saying, I got here, and he goes off and does some unrelated work. The second man out sees he's the second man, the job is now done, and he carries on with the next.
As if he were the first guy, for example.
Yeah, as if you were the first guy, yeah.
And the way the link, and it's been several years since I looked at Go, so forgive me if I'm pulling this up wrong, but the way the Go routine works, it appears that it could actually, the Go routine could get ahead of the consumer of its results and continue to execute. So it's not an interlocked, it's not necessarily an interlocked one, then the other, then the one, then the other. So it's not like a function. Because you could potentially queue the results. Does Go use yield from Go routines? Is that correct? Does anyone remember?
This I do not know.
I think it yields results, not returns results. Does that sound right?
It uses channels to communicate between them.
Usually use channels to communicate in Go routine.
That's right,
Yeah.
it channels.
Okay.
So the channel could conceptually be a, it's been a while since I've looked at it, but the channel could conceptually be a buffer that's local to that particular core.
Surely a producer-consumer queue arrangement.
Yes, but it
Yeah.
doesn't have to be a blocking queue.
If it gets full, it does.
Yes, of course. Yeah.
No, these are always, you know, the race is on. Your queue is either always full or always empty.
Yeah, but I believe that the
This reminds
current
me of Cliff's podcast episode on queues.
Yeah.
Yeah.
Yeah. Sometimes your queue does the right QE things and comes full and empty and bounces around, especially if you have irregular workflows. But if you have steady state, your queue is either always full or always empty.
Yeah.
Cliff, do you plan to add to your podcasts?
I should, huh? I've had other people
run through all of them, and I think
you know, what happened was I got into this compiler research thing, and I was trying to wait till I had a definitive answer before I started podcasting on it because I didn't want to talk about shit I wasn't sure was going to work. So, but now I've been at it for like 6 months, and I've had all kind of cool results, and I don't know how to express them. Like I can do kind of a really amazing shit with more or less glorified constant propagation and lattice theory. How it correlates to language implementation design is a little fuzzy yet because it's not there. But I'm totally doing, you were talking about closures and uplifted whatever closures. Yeah, I'm totally looking at all my stack frames are closures in the typing system, and I do escape analysis and alias analysis in the type system and discover that you didn't actually escape, so now you're back to being stack allocated. And I'm doing, you know, type inference from hell on this whole thing. And it alternates between cooler and hell and like scarier than whatever, and weird things work and don't work. I can do amazing things that you can't get out of any other type system. At the same time, some shit that's really easy, I'm having troubles with, right? And that's because and so that's why I haven't podcasted. I'm like, I don't have a definitive, it's definitely going to work, it's definitely not going to work.
So one of the episodes in there, you mentioned the rocket school.
Oh yeah, yeah, it's another one people keep asking about. I probably should start that up again.
Or maybe you can take some of that content and put it in the podcast. You know, that's
some of it does.
Have like a teaser in there.
Right, some of it does. You know, I talk about shit like bandwidth. Somebody said,
"Hey, no, that's why the podcast is so great, right? You're hungry for more."
Okay, all right. Food for thought. Inline. So hit some limit. What's the limit of inlining? It's actually good pivot here. I'm going to pivot on this, Cameron. There's a lot of rules on inlining, and different JVMs do it differently. I'll tell you fairly well what C2 did 15 years ago, and the Azul folks are using LLVM, which the rules are probably different. So, and if you're using Scala, they do a lot of hand inlining themselves before they hand off bytecodes. But when you get down to bytecodes, there's sort of a hierarchy of things that happen. We took an overflow counter to decide we were going to compile. We crawled the stack looking at execution frequencies until we find what we view as a good compilation point. The set of things we crawled get flagged as thou shalt inline these. And then you start at the top and you go down looking at the bytecodes at all the invoke calls and decide case by case to inline or not before doing any other analysis of things. Those inlining decisions are based off of statically known types, off of sometimes we do a little bit of analysis and see some known pointers, especially nil and zeros and trues and falses. And then we decide if you're an accessor function, sort of all bets are off, we're going to inline you. So that's literally a load or store wrapped in a function call. If you're sort of smaller, there's one threshold that says if you're fairly inexpensive, we'll clone the code. Then there's a medium size limit that says if we haven't compiled you already, we'll go ahead and inline you now. But if there's an inline version of you floating around and we start making lots of mid-sized things inlining, we'll blow up the iCache. So at some point, we'll stop inlining there. There's a frequency-based argument that says your high frequency, the method you're calling is low frequency, therefore a loop wraps you. That's a very strong indicator that's good to inline. And then there's blowout on, we got too many bytecodes, and we suspect we are going to not get further improvements. And or we'll blow out iCache, or we'll blow out compilation time. And so there's a limit of like 10 or 20,000 total counts of bytecodes that get inlined. If you have a single large function that exceeds some threshold like around there, it just won't get JITted at all. So that's only a case for machine-generated functions. But you can have machine-generated code that fails to ever inline, it fails to ever compile because it hits some threshold. So there's start from some overflow count and crawl the stack to see a frequency change that you decide is sufficient to say, I'm going to compile here. Those get compiled. Accessors almost always get compiled. You stop at 8K total bytecodes. You do otherwise inline things that you can do class hierarchy analysis and decide you have a single target. It's okay if you have two targets and they're both sufficiently common. We might inline them both with a switch to tell between them. And rarely we'll inline a common hot guy of a megamorphic call and put a bailout test to go to the megamorphic side if it's the other variety. Like if a call appears to be 90% one guy and 10% like 1,000 things, you'll get the 90-10 split of one inline, one not. And after anyone's inline, we recursively walk inside that guy and inline again using the same technology, which has this issue that the first things in the top method tend to get inline to their limits of execution frequency and knowledge. And the tail half things can hit the 8K, 10K limit and fail to inline unless they're an accessor. So there's some screwball things going on there. That's sort of the main pieces though. The major fail, so there are minor tweaks you could definitely improve, including have all kind of compiler knowledge before you start inlining. But the major fail is if you have a megamorphic call in an inner loop. Because it's megamorphic, it doesn't get inlined. It's commonly the case in sort of more modern programming languages that are built over a JVM, so Jython, Python, Scala, Clojure, these kind of guys, that they have these megamorphic calls, typically implemented as interface calls, but any given loop goes to only one, not to the megamorphic 37. Because it only goes to one, you'd like to clone that loop for the class of the inner vcall. And then have a bailout that says, and all the rest go that way, but there were never more, all the rest, so I don't care. And then the one loop has the one guy can now be inline, and if you inline inside the loop, that's your big win. If you fail to inline inside the hot loop, that's your big lose. And so that's sort of the major limit of the current C2 inlining strategy. And then you know, LLVM does something different.
Yeah, I would say the main differences compared to what you described, what we do in LLVM in Falcon, because our inliner is significantly like changed compared to vanilla LLVM. So they do bottom-up inlining. We have to do top-down with some bottom-up elements, just because we are given one compilation unit and we need to explore the call graph, which is reachable from there. But we are looking at IR level candidates. So we look at candidates which were already pre-simplified. We look at the cost of inlining, which is the size of inlinee after inlining, and at the benefit, it's a different simplification which will happen after we inline. In order to see that, we look at the arguments passed, and if we see exact types, constants, new allocations flowing into the inline candidate, this is we see it as benefit and increase the chance of inlining. Yeah, things like devirtualization, we slice the problem slightly different. We have devirtualization as a separate thing from the inlining, and things like having a megamorphic call inside of a hot loop, we would do profile-guided devirtualization. We would have this type switch. We would probably do loop on switch just based on the fact that, okay, we have a loop and we have invariant condition. We can create several copies of the loop. Well, and after that, our inliner would go and inline the call sites, which are now direct in each and every loop.
Yeah, it's a major difference with hotspot. Inlining is done before the major optimizer kicks in, so it's just frequencies and what the interpreter knows.
And also we
don't loop on switch yet. I mean, I loop on switch for single target ifs once. I do not do loop on switch over, you know, megamorphic call site. Or I didn't, I don't think, and I don't believe Oracle has done since I left.
Yeah, another thing, we have a priority queue for call sites. Because we have an estimation of benefit for call sites, we can try to inline those which are more beneficial earlier, so we don't hit the total threshold.
Yeah. Oh, there's a bunch of improvements there. Does that answer your question? Well, how about this, Mohammed? Why did you ask? What was your goal? Mohammed? No mic. Okay. Are you chatting? But I can't tell. Okay. Well, let's roll on here. If Mohammed comes back, he does. There goes. Playing around the inlining at the moment. Do you have a mic? It's going to go faster if you mic it. But fine. What are you playing around with the LLVM, or are you playing around with C2 or with something else? Yeah, I had to call my wife to chase the cat off. Yeah, I totally get it. Playing around with JVM. So I think that's the like OpenJDK. So that would be the C2. Yeah. The major win is a major hack, which is do inlining after the C2 major iter pass has done all this type analysis and tell you what the hell types are, as well as found the loops and tells you what the hell the loop nesting is, and then you go look for the hot inner loop and decide what you're gonna do. I think I put in loop on switching for one if, but if you want to do a switch-based loop on switching, you got more work to do. And you have a bunch of work because you have a code blowout issues you have to deal with and such like that. There's a game there where you want to declare, you'd love to know what this class of this function called an inner loop is, and how high up the call chain do you have to go to where that class becomes a compile time constant. And that's where you want to inline from. And I don't want to hear that coming out of the LLVM either, but that's sort of the ideal thing. And I don't know if that's possible or not, but there's something there that says, I want to do something smart. At H2O, we had the same kind of issue, and my theory never implemented was I was going to basically manually inline these loop bodies with a class variation for each of the different inner loop function calls, because I was already doing code gen for all kinds of stuff. All your cross cluster things were all code gen for serializing, deserializing. So adding another one for doing method call would have been sort of straightforwardly. All right, what do you mean by manually? Oh, yeah, in Java, it's class for name. I picked up Java assist, but there's a dozen of these things. You write some code, you write a string, that's Java code, inside of Java, running Java VM, and you hand it off to Java assist, and you get a class object back. You make a new object, and you make a function call on it. So that's manual code gen. So in the case of, I have a hot inner loop of a very complicated iterator that does a distributed global scale out iteration and merge back. It's a very complicated iterator. It's iterating over a 2D array that's bigger than one machine. So it's a cluster-wide 2D array. I have a loop body that's written by a mathematician that does something, God only knows what. It does Cox proportional hazards, or, I don't know, there are 1,000 of these things. It's pretty straightforward code accessing a two-dimensional array. The inner loop is virtual because it's what the mathematician wrote, and there's 20 mathematicians writing code, so I have hundreds and hundreds of these. It's virtual because my compression strategy varies by column. So I have a dozen compression strategies active at any given time, but typically there's only one blend of virtual calls. So after I make 5 or 6 copies, where each copy is specialized on 20 different virtual calls, I'll have all the virtuals devirtualized with a minimal number of copies of code. So then I would go to Java Assist and say, here's a Java string, and it has a map call, and the map call takes the following classes for objects that have precision known types so that I can do perfect inlining in them. And my complicated iterator starts by querying the types of the compressions and the class for the inner loop of the mathematician wrote, and he looks in his cache. And if he doesn't find his cache, he builds a Java object with the right string and goes to Java system, comes back to the class object, and throws it in his cache. Now he's got his cache, he pulls up his cache and says, make a function call on this object. And I'm guaranteed that object's going to iterate over 100,000 things with no virtual calls in the inner loop. And that's going to give me a good 10x speed up. So 10x is worth it, especially on a big data thing. But that's me doing manual inlining. Yeah, I can't. No, not force inline. That's different. Force inline doesn't clone code, and the key operation here is to clone the code. Like, what's it mean to force inline on a virtual call that goes to 20 targets? Which of the 20 targets do you inline, right? Which ones got forced? All of them, maybe? Okay. As soon as you do all of them, you blow out your iCache and you lose. So you have to do something smarter than that. Same problem bites all the Python, JRuby, Clojure folks. They have to figure out how to make their calls not look to the JVM like a mysterious megamorphic vcall, where the typical thing they do is they have some proxy object for a function that they load a pointer out of and make a call on. And from the JVM's point of view, you loaded an object that's got a base type of, Clojure base object and has a million subclasses, and you made a vcall on it. And so it looks like a giant megamorphic call, so none of them get inlined. And so you have no inlining, and so you suck because you don't inline. Sort of the canonical problem with the current strategies of the JVM versus other people's calling conventions. Been this problem for a decade, so it's a good problem to tackle. It's time for an answer. Okay, it's awfully quiet now.
So Go has all these set of rules to inline its own functions, and I was dealing with some code. I'm trying to figure out what these are and calculate some kind of a complexity value for each function. And I think I probably am mistaken, but there was something that if I used a switch in the function, then it's too complex to inline. So it's, I wish there was some like transparency around this other than, it could be a moving target because,
it should be a moving target, but they have their inlining heuristics, same as everyone else. It's always a heuristic. There's no perfect answer.
That's true.
The issue is, unless you're studying the domain of what the compiler does, it's hard to make localized tweaks that are reliably performant. Like the compiler will get all the easy ones. As soon as you have subtle things, unless you're doing a trial, trial and unwind and redo, it's hard to guess from the outside in whether it's a win or not. Because if you inline a big ass wad of code, you only save the caller overhead plus whatever you get from having the inlining allowing more optimization, typically hoisting out of loops.
Mm-hmm.
If you didn't get it hoisted out of a loop, you didn't get any win. But you definitely lost an iCache size. So if you try too hard to inline, you can blow out your iCache and you will suck bad time.
But it kind of seems like write small, less complex functions seems to be like the...
This is, no. People write their code. This is why there's Clojure. This is why there's Scala. People want a different way to write than Java, right?
Sure.
So you write code in a style that is wildly different from person to person, and what you consider more or less complicated is somebody else's, bread and butter, or I hate it, or whatever. The compiler gets it all and sees it all. And sometimes you write tiny short pieces of code, and he all happily inlines, and it's all good. But sometimes tiny short pieces of code just do not express your problem state very well. And so you just don't want to write it that way. Or you want to write it in the Clojure language, but there's no easy mapping from Clojure to JVM bytecodes, and there's no easy mapping from Clojure to Go routines, right?
Sure.
Or to Go bytecodes, or whatever the hell Go's using. Because there's no easy mapping, the mapping is very conservative and stupid, and the compiler, the Go compiler, for instance, can't discern through the mapping, understand. He loses all the type information that was present and available otherwise, and he writes suck-ass code. So this is the classic problem, right?
Sure.
So it's easy to say, hey, I'm only going to write code that looks like this, but that's not what actually happens. I myself know how to write Java code that I know damn well the inliner will inline, and I'll get the performance I want out of it. But that's not a scalable solution.
True. So on like a completely unrelated note, has anyone read the paper that Facebook published? And it's apparently a deep learning model to translate between languages like Java.
Throw the link into the chat.
I'll do that. I'll just look it up. Apparently, I mean, I think it's like far from, like, it doesn't obviously understand runtime or anything. It's probably just a syntax.
You know that Facebook has made it to the realm of the big fat CAs and Oracles and Microsofts when they have people being paid to write these papers.
What are you going to do, right? The Bell Labs did fabulous research for many years, funded by big telcos. So,
funded by the public.
Well, by the monopoly that, fine. Yeah. So, I don't know. Is Facebook funded by the public?
Hey, I'm not complaining. I love these papers.
They're not funded by me, but that's okay.
Just because I'm making fun of them doesn't mean I'm complaining.
Okay, good. Yeah, no problem. Yeah, right. I mean, there's some fun research that comes out of these folks. There's no question about it. Facebook Ai Transpiler. There you go. Okay, that's a great title. I will click through that. I'll just click through it now and get my browser and come back to it. Stare at it in a minute. So this is just an effort to like do a reasonably better translation job than the obvious one. This is probably the main grief is the obvious translation is locally always correct and globally sucks because it loses all information.
I think their main the main interesting thing here is that they didn't need language pairs to like train. They used some kind of an auto encoder to train them.
Yeah, I'm curious to see what their quality of translation is. So you're saying to me that they're not semantically correct? That they did a AI based.
When they're translating between the two, I don't know if they'll understand. Honestly, I don't know.
Okay, fine. Yeah, that's fair enough. But, I see people do games where they say, yeah, we can make this look like a that, and it's pretty close, but they lost the semantic translation, and then that's just a fail.
Yeah, like the standard libraries and the runtime, that would be hard to predict. Like use a sync map here or use whatever.
Yeah, those are subtle. There are simpler ones. Those kind of things can blow up.
And especially they're not programming. They're not training it on like a pair. They're not saying this is how this looks and this is how that looks. And they're same. They're not doing
right. So if you first did a translation that was sort of semantically correct, and then you went back through and did syntactic sugar corrections to preserve something, I imagine the AI might be able to pile in there.
I mean, they could probably have multiple models, each thing kind of going layer by layer.
Yeah. Well, I'd read the paper and see what it does. More, links for LLVM. Okay. Yep. That'll keep me busy. Well, I'm gonna go do my compiler thing at some point here. I should probably come up with like examples of shit I can do and shit I can't do for another go round. I think you'd be entertained.
Yeah, give us a dry run of your future podcast.
See, here we'll do something. So functions are always anonymous and just be assigned to a variable. So I'm going to write something that's a little more complicated to show sort of what I can do that's really cool. So,
yeah, live coding sessions are always great.
You can always just share your screen, Cliff.
Oh, I'm just typing out of the blue here on the chat. So here is, so let me actually do a little easier one here so people get the idea here. Okay, so square is a function that takes an x and produces an x squared, and it's ambiguous as whether it's a float or an int because multiply is a primitive float or int. And that will go in all contexts, so either floats or ints go in, and then it'll bake down to the right thing. The gen call has a no arg function, so there's no arrow. Count is a local variable. It's initialized as 0. It's returning a tuple, which is the parens, the round parens. The tuple is a pair of functions. Count, which is the return value of just the count variable, and count plus plus, which is incrementing it. So then I can say,
So I want to return the same value twice?
Yeah, so this count B, that's an inc B. So gen makes a counter. So I return a pair of functions from gen with a private counter. And so if I do inc A, I bump A's counter. Oh, sorry, my auto capitalization and Slack is biting me here. And inc B will auto inc, increments B, and they're different. So if I inc A again and I go type count A, I'm going to get back 2 for A and 1 for B. So they're real closures as upwards exposed fun args. But one of my goals is conciseness. So you got something very tiny and small for the gen returning a pair of functions, being a function that returns a pair of functions. Otherwise, the expression syntax is straight up looking like C code or Java code. It's almost totally identical.
So what's the CNT semicolon part? Is that the argument?
That's a local variable named count.
Oh, I see. All right. Okay.
Because it has no assignment value, sure. I will look for count like Python does up in the current global scope. And not finding it, I'll declare it a local variable in local scope. So you can assign things in local scope and that will shadow. If you fail to assign something, you read it before you write it, it's a read now. So the first reference in a scope does a decision if you're talking about local or global, same as sort of like Python does. So I made a local variable and it's initialized to 0. And then I have it return a pair of functions, one of which is the value of the variable, and the other one is the plus plus in the variable, which is actually give you the value of the variable as well. There are all functions return values. Everyone has a value. Everything has a value.
Yeah. I can see why, there's so much in that short bit of code. I kind of like that. So.
It's kind, like I said, it's kind of fun. I can do some fun shit. Let me show you. So let me show you a map call. So
do you have like a ternary operator too?
There's a ternary operator, yeah. It has a short form if you don't care for the other side, it just returns a 0.
Oh wow, that's.
So let me do okay. So tuples so tuple syntax looks like that. Does it have any back? It doesn't have any damn. I might have to switch to my screen share on my editor. So .0.1 after tuple pulls up the 0 or the 1 field, right? So that'll give me a string, and a .1 will give me a 3, right? So just how to get at it. So here's a map call. It's going to take a function and a list. I'm going to type things out a little bit so it's a little easier to read.
And you have like a REPL for this right now? Or?
I have a typing system that supports a REPL, and I can run expressions through and type them. I don't have an execution engine because I'm still screwing around with types. And I go back and forth whether I should stop and go make an execution engine without types, just so I can have a play with it model. I'm close. I could get a REPL out probably in a couple weeks. And it might be
whenever you need the rest of us to play with it, I think.
Yeah, you could actually play with it. It'd be super slow because it'd be interpreted only, right? Furthermore, it wouldn't have all the strong typing, so it'd be doing type checks on the fly, which is not the goal of the language. Okay, so when you have a map call, you ask, is the list empty? That's your ternary operator. And if it is, I'm going to return a 0, and that's that. And then the body is a tuple, which consists of running map on the same function and the tail of the list. And the other half of the tuple is the value running the function on the head of the list. We should do the head first and the tail second, a little better here. And I possibly blew it. So map is a variable that's assigned a function. The function takes 2 arguments, fun and list. List is null checked. Then that's the question mark. There's a :0 at the end. That's the fail out. I didn't have anything in the list. List was empty. If the list is not empty, then I return you a tuple, that's open paren, of map called on function and the head of the list. So it just changed down the list. And the second half of the tuple is the function applied to the second element of the tuple. So assuming the tuple represents a linked list chained on the first element, this is a map call. And I will correctly type this all the way down the line, including knowing for a fact that list is a recursive type that refers to itself as a tuple-based type. And it will be suitable to apply it to anything that has types that where you have two or more fields and a function that matches the type of the second field.
Sorry, I didn't
Type of
quite
first
follow
field
the A3 is a tuple and the .0 is a null check.
The .0 is get the 0th element.
Oh, okay.
Just like a field. So if I want to make a struct, so here
so
is
two ways to get the numbered element. So. Okay.
No, the second example, I was just responding. That's not Cliff's.
Oh, I see.
By the way, I think the map example, the map call should be on the tail of the list, right? I think it's on the head of the list currently.
Well, I'm chaining through the head of the list, and the function's on the tail of the list because the function's on the tail, the second half. So the list looks like, let me write some list here. And the list ends with a null, and I have 3, 4. So here's a list. There's a set of lists, set of tuples nested. That the list ends in a null on the first one, and the 3 and the 4. So I could do map of a square, right? And in my list here. So that would apply squaring to a list of 3s and 4s and return me a 9 and a 16 in the list. And you could swap 0 and 1 to point the list the other way around. No, OpenFriend's a tuple. And so I don't have a specialized list type. I have tuples, which you can make a list by just chaining the tuples together.
Yeah, I just thought to dive into the rest of the list, you would have to access the second element and not the first, because usually the tail of a list is the rest of the list, right?
Yeah, I could redo the list the other way around and change the map call to do list.1, list.0 reversed, and that would work too.
Yeah,
it's totally symmetric.
Just a little confusion about the
Okay,
code.
so you would like to see the list chained through the tail.
I'm expecting Lisp to jump up at any point here with cons and.
Right. No, I'm doing these kinds of examples to show that I can type recursive functions, because that's the current grief in life is recursive functions and closures are giving me grief. So that's where I'm at. But I'm nothing Lisp-like about this. This is otherwise completely C-like syntax, except all types removed because I can totally infer them. Point there is me assigning a type to a structure with an X and Y. But I could totally pass an X and a Y into my map call if I happen to have X being passed in elements of point, not as in integer or the typical point-like things. I can declare a point to have stronger types than just X and Y. So I can make it be, point have integer X and integer Y, but I don't have to.
Okay, cool.
So I could just keep colon type is a type, and you can put them anywhere. You can type functions, and you can type parameters and return values and arbitrary expression elements and all that kind of shit. And all I do with those is I validate that they are correct when I'm all said and done. I type your program without your type annotations, and then I validate it's correct when you're done. And that's sort of one of my main goals is to do real type inference. So there's all kinds of other things going on here that happen. Like I can recognize field names and parameters and sort of duck-like typing everywhere. And as long as I get a type out of it, I'm happy. And dead code, I will, if I can syntactically parse your dead code, but I know that it's dead in the type system, then I'll ignore type errors in it. And that lets you write shit like if def Darwin, if def Linux, if def Windows,
So one of my favorite features is I call to do, which is if you're in the middle of something and you're like, I just need to have the compiler ignore this, instead of pound if0, you just put a to do, and the rest of that block is ignored.
Yeah. Yeah, and for me, if I wrap curly braces around anything, it becomes a function, which if you don't call, it's just like a value to be ignored. So I can basically thunk anything by just putting curly braces and walk away. Has that effect. So yeah, so I'm writing shit like Darwin ? And there's some recall, and Windows ? with recall. And if Darwin and Windows evaluate the truth or false, then if they're false and you have incorrect argument counts, for instance, I'll ignore it because it's in dead code. So this is sort of type safe macro concepts floating around. I have final stores instead of final fields. So you can, deserialize things with finals and make them final syntactically in the language without having to cheat. Java has to cheat around deserializing the finals. And because it's just more convenient, because I want to make a loop that I want to be all final when I'm done. I want to have a final store, not a final field. And there's a bunch of other stuff. You have to go to the AA website and you can go to README and get a bunch of little tiny examples. And if you go to the test side of things and you can go to the test parse, you get a lot more examples. But most of them are small. They're just testing error codes and error conditions and simple, I can do this and that kind of things. So a REPL would be what people, let me see if I can finish out my closure branch and fold it into master, and then I'll make a REPL. It's time for a REPL. I want to play with a REPL too. I'm writing larger pieces as test things, and that's like really fun, but I don't know how well it's going to work until I can write big things, even if they run super slow and they fail to type check correctly. I don't care. I just want to run them to see what it looks like to write the code.
I see you prefer like really compact code, which is, I think I prefer it too.
That's a different rant that I do in public too.
It's kind of funny. I do enjoy Go, but I wish it was more compact. That's kind of how.
Exactly. Well, I'm writing this in Java, and I'm just so annoyed at the volume of repetitive typing that has to pop out.
But it's kind of funny how Java itself has a brand of being really verbose code. Like,
it was so much better than what came before, and yet.
You guys are so funny. You just got to learn how to type faster.
Exactly. Well, auto completion, this and that. I'm pretty good.
I measure myself by lines of code, and I count the blank ones.
That's what I'm counting. I'm counting lines of code. Comments count, whatever. But the actual act of having to go hit autocomplete on the goddamn, I do an instance of, INST autocomplete. Okay, fine. TYP, I got 27 node types. So I do 3 more letters, autocomplete. Okay, just did X instance of Y. Why do I have to do the Y again to cast to use the damn sucker? No, now I have to open paren again.
Yeah. No, the worst is you need 2 sets of parens because as soon as you instance of, so you have a screw up with the precedence table to start with.
Yeah.
Then you need 2 more sets of parentheses because you have to cast it, because you're going to, whatever the result of the cast is, you're going to dot something on the end of it. So you need the outer parens around the cast, and the cast requires its own set of parens. And by now you're at a column 137, and
Exactly. I fixed that in my language. I will totally look at the if test and pick up on any obvious short versions of this is a that, X equals Y, X equals 0, not 0, instance, not instance, and immediately the true or falsy branch knows the stronger type. So that's one of the shortcuts,
Yeah, so you do type flow basically.
Yeah, type flow stuff here. I don't have picked out an instance of test here. So I'll fake a syntax that's not legit here.
I just wanted to say the need for the additional cast has been fixed in Java 15.
That was 15. I'm on Java 8, and so is like half the planet. Fine.
It's moving along. It's moving along.
Okay.
8.
There we go. So if P is a point, then I can say, P.x, not X.x, P.x, because I know it's a point. And otherwise, you do something else. I can take variable declarations anywhere. So distance is equal to X equals something something times X plus Y equals something something times y, like that. So you can just declare a variable on the fly, and I'll take it, and then you can use it later in the same expression. And all straight up equal signs are final assignments as well. So those are all constantly to the end of the scope.
I can see my functions being like just a long ternary operator, one
Yeah.
inside the other with like allocations and assignments.
Yeah. That was kind of the goal, is to get things to be pretty damn tight. That goes to my rant of fluffy code versus tight code, which I'll not do now, but that can happen next go around. But I see, like, lunch is appearing, and it's been an hour and a half and a really fun time. So any last comments before I say let's meet again next week?
Language looks really interesting. Please continue with it.
Okay. Well, I'm encouraged. I will certainly continue with it. Yeah, go look at AA, GitHub, click AA.
I have
and
actually.
Throw out any comments you want at me. It's all work in progress, so everything can be changed at this point.
All I have to convince you to do is to use our IR, and then you'll have to write the VM for us.
Yeah, eventually I'll need a VM of some kind for what I'm doing here. I haven't figured out where I want to go there. I started in this path because there's no good language for doing data science in. It's either Python or R, both of which have horrible problems. So I wanted a better language for this stuff. All right.
Julia, that's
Swift is interesting, I think, for the data science.
How many Swift programmers are there on the planet outside of Apple?
Oh, that's cheating. That's cheating.
Exactly. Now, how many AA programmers are there outside of Apple? Yeah, okay, one. Fine.
Although the project is from Google, the Swift from TensorFlow, at least. I do find it far more interesting than Python in any case, because it's pretty much the syntax is at least as compact and the typing actually works.
It has a typing system.
So keep in mind that Matt won't tell us where he's going to work, and he likes Swift. So I think
not Apple. I can say it's not Apple.
Oh, yes, I will continue with innovative uses of lattice theory. I've gone pretty far down the lattice theory rat hole too. I can probably put some papers out on lattice theory now.
I do like, just going to the data science aspect, seriously, one aspect I do like, and I do think it's still kind of missing, is this differentiable programming thing. So we actually have built-in automatic differentiation in Swift from TensorFlow. So if you would just like to compute the derivative of your function, you can. And you can also compute the derivative of a C function that you are calling through FFI. And that I do not see in any other languages right now.
Are you actually symbolically differentiating, or are you?
No, it's algorithmic differentiation. It's reverse mode and forward mode, including, I think, the higher order like Hessian. And it's pretty good syntax for that, and it is in a pretty well done in the type system.
Is it in the type system as opposed to being in a operator overloaded?
It's built in the program. It's built in the programming language. Let me see if I can find this.
Interesting.
Let's see.
Yeah, I'm going to hang on for a link.
Yeah, Chris Latner talked about it in one of his podcasts, so I remember.
Oh, I see. Okay. Link. Not that I'm impatient or anything. It's my classic fail.
Yeah, wanting to build this apparently was one of his reasons of moving from Apple back to Google. So.
Oh, really?
$2 million didn't hurt.
Yeah. That is. There's a thing there.
Okay, so the link is there.
I'm no longer beholden to anyone else's money, so I can do what the hell I want. But had I needed to have my bills paid and Google would let me write new programming languages, that would be a big draw. No doubt about it. Here we go. Da-da-da. Function f, derivative of is your syntax of a function argument. And oh, you're defining it? Or you have to define the derivative, but you declare it as a derivative. I'm confused. I thought you were automatically.
So you have a function f, you see, and the function f is just x times x.
Yes.
And then you are interested to have a derivative of this f. So
Yeah,
from this
I
point
would claim
on,
that it's not the derivative of f.
so df dx is now another function that is going to take an argument and return you the derivative value at that argument. So df df is a function itself. That's a gradient of f, basically.
Right.
And then you call this gradient with argument 3.
I'm sorry. Okay, now I see what you did. Okay, fine. I'm sorry. I was thinking it just line wrapped on you, like a bunch of my examples line wrapped. But no, you have three. You have a bunch of lines. Let df dx is one line, and using df dx with 3 is a second line, which totally works.
Exactly.
And //6 is not integer divided by 6. It is
exactly. It's just a comment, yeah. You just need this attribute for differentiable.
Let us claim that Zoom group chat is not a very good way to express code snippets.
Yeah, it should have markdown on something.
Maybe I do.
No, it doesn't have markdown.
A Skype chat parallel, because at least I can triple quote in Skype and it'll declare it a programming syntax. And quit auto capitalize. I said Inc A and it was Inca, so it auto capped to I. But Inc B was not Inca, so it did not auto capitalize.
Or you could use REPL.it, turn on their Swift REPL, and then just kind of send us a link.
Oh, there you go. Oh wait, who's doing the damn? I just have it on my links here. There was the compiler explorer was also taking.
REPL.it is like the best. It's
Godbolt.
Godbolt. Yes, it's on my links. Okay, fine. Yeah, but just having Swift REPL for Swift, absolutely. Yeah. All right.
Yeah, I was using Godbolt this week. I just found that.
It's kind of a fun toy. I wish
There's also Swift Godbolt.
6 years ago. Right.
Yeah.
It does a bunch of languages. Yeah. The thing I did that I these days would be done the way Godbolt does is the super optimizer for the GNU folks. It was all these little tiny compiler, like stupid code things for stupid code tricks. You ran through the super optimizer, especially in an x86. I don't know. I'm sure it's still around. It should be a web interface for that thing. That would be a fun one to have too. That's
the super is pretty interesting. So I know that it's from John Rager. It's the same author of that LLVM blog post, and I think that may still be working. It is for LLVM.
What is the super optimizer?
Super, yeah. Let me see if I can find the GitHub for that.
Synthesizing super optimizer. Yeah, okay.
23 days ago, there we go.
Huh. I'm curious now. Okay, fine. Yeah, the one I was using for GCC was simply to get me the minimal x86 expression to do something, flow-free EDM for testing, blah, 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 min, max of a couple things, or I don't know, there's a bunch of varieties he kept screwing around with. And he always came up with something really fun that turns out, hotspots, using them forever and a day. Yeah, okay, well, this has been a great session. I had a lot of fun. I got too much reading for next week. We all got our homework to do. I've got requests for Rocket School, requests for a podcast, which is probably going to happen. No, let's see. We'll see what we can do with podcasts here.
There is one very interesting paper. I just posted this one. It's from CGO this year. It's called Generation and Optimization 2020, testing static analysis for precision and soundness. So this actually is a super optimizer to test the optimizations in LLVM to see if they are the best precision they possibly can be. And they actually found pretty interesting results for this. Like even in tracking demanded bits, if you are having some integer and you shift this integer n bits to the right, then you will never need those bits that were in the lower n bits. And they can actually track those things. There had some precision issues in LLVM, and they found those issues using this super optimizer. So it's pretty interesting.
I want to talk about that one next week.
I'm sorry?
I said I want to talk about that one next week because I have this idea of A/B testing in a hotspot style compiler. So you basically gen two different paths and compare them as they run.
So back to the precision point, the analysis I'm getting out of the lattice theory is by construction and design, guaranteed perfect precision everywhere. And if I fail a screw up, I get slapped on the wrist pretty quick. So I know for a fact that I have the perfect precision, use, life, death, information, but also the quality of analysis is symmetrically, I don't know, the next week, there's some fun stuff there, but there is a thing where you can get perfect precision in an efficient analysis using lattice theory. Okay, done. I will throw this up on Twitter as a link as soon as it comes. Next week, we've got our hands full of things to talk about with all kinds of cool stuff. I'll still have to stare at what differentiable does, but that looks like fun too. It's been a great session. I love it. See you next week. Bye-bye.
Yeah. Have a good weekend. See ya.
Bye, guys.
Bye.
Bye.